So I think we'll get started. So this is one of the air quality talks that we're going to be discussing Fairbanks air quality. And I'd like to introduce myself. I'm Bill Simpson, and I'm from here at UAF. I'm in the chemistry department and also with the Geophysical Institute. I'm one of the organizers of the FairAir project. The FairAir project is a NSF-funded project which is aiming to understand air quality under cold and dark conditions, the conditions of Fairbanks. And it's a project that you can get involved with. It's really grown up from community interest in air quality in the area. And we'll put the link to the website into the chat, and you'll be able to see that there and look around the website and see what we're about, and you can see about how you can get involved. This project has really come out of community interest. We've talked with the community about air quality, and we've often heard concerns from the community. And this set of talks that we're doing this winter is really coming from community concerns about indoor air and things like wildfire smoke. People have often asked these questions. And this set of Zoom talks is trying to address some of those questions with experts on those fields. So we're going to have 3 total talks in the series. The first talk was given 2 weeks ago by Professor Delphine Farmer, and she talked about indoor air quality and things like cleaners and cooking and stuff like that. And she gave a great talk. If you go to the FairAir website, you can see a video there. And then you can also see some questions that were asked and answers to those questions. So after this talk, you can also go and look at questions if we don't get to all of them at the end. So this talk will be Professor Peter DeCarlo from Johns Hopkins University, talking about the origins of particles indoors. And I'll let him tell you about that, and just tell you the last talk will be about wildfire smoke and health, and that'll be given by Professor Emily Fisher from Colorado State University. Just a little bit about the operations. We're going to have Peter give his talk, and then after he's done with a presentation, we're going to open it out to questions. The way we want you to ask the questions is by putting them into the chat, and then you can get the question there, and we'll just filter through them and read those questions out. Additionally, if you're watching on Facebook, put the questions into the comments, and we have people watching the Facebook stream to bring them over to Zoom so they'll get asked. And as I said, if we run out of time at the end, we'll try and answer your questions and put them up on the FairAir website. So go look at that after the fact. So without any further ado, I'm happy to introduce our speaker, Professor Peter DeCarlo. He's going to be in Fairbanks in about a year for the field study that we're doing as a part of this project, and I'm very excited about that, and I'm very excited to hear what he'll tell us about now. Take it away, Pete.
Thanks, Bill, for the introduction. I'm going to just get my slides up. Can everyone see them? I hope. Good. All right. So my name's Pete DeCarlo, and I hopefully will give a talk that will prompt some questions from you guys. And I'm happy for you guys to throw into the chat questions that come up along the way. If there's something that I need to clarify in a little more detail, feel free to let me know, and I can try to do that. The purpose of the talk today is to kind of synthesize research that I've done in my group in other places in the world, looking at not just indoor air, but also outdoor air and how that may affect indoor air. The indoor part is actually something that's relatively new for me. I started thinking about that, I guess, maybe 10 years after I started thinking about outdoor air. But the reality is, and I think this is what Dr. Farmer mentioned in the talk 2 weeks ago, we spend an awful lot of our time indoors. And I'll get to that in a bit too, but that means that our exposure to outdoor air pollution actually happens in the indoor environment too. And so this picture just kind of encapsulates a lot of what we've been thinking about in my group in terms of indoor air. I actually added this wood stove in the lower corner here for the purposes of this talk because we haven't had a chance to study that in detail in this context yet. And I'm really looking forward to being in Fairbanks to be able to do that. So, to start this out, as Bill mentioned, had COVID not happened, my group would be in Fairbanks right now making measurements. And I'm really looking forward to doing that next year to answer some of the science questions that we have about what happens in this interplay between outdoor and indoor air. And I think Fairbanks is a pretty unique environment. I'm very excited to see that and be there for that. So this is a picture of the purple air network that you guys have going in Fairbanks, which I still looks at every once in a while just to see how things are going. Certainly a little bit different than where I live currently in Baltimore. So I just wanted to start out in just kind of general information about where our indoor particles come from. And I focus mostly on particles because we know that these tend to have a larger health impact than the gases that we breathe. And we know that from outdoor studies. And again, this is something we want to learn more about in the indoor environment and how those might also impact us. And there's really three general kind of ways in which particles come into being in the indoor environment. And the first is infiltration. Infiltration simply means coming in from the outside. And in a home environment, this means leakage in your house. If you put your hand close to a window, sometimes you can feel some cold air coming through. That's basically cracks or openings in the building facade or the outdoor part of the building, letting some of that air come in. And with that air that comes in are particles from the outside too. So infiltration is one of the key ways in which outdoor air and outdoor particles make their way into the indoor environment for us to breathe. Another way in which particles come into the indoor environment is through direct emission. So if you're cooking on the stove and you're frying something, a lot of little particles are generated in the act of frying your food. That gets into the air, into the indoor environment, and is something you can breathe. In the context of this project that Bill mentioned that we're really looking forward to doing next year, wood smoke. If you have a wood stove or a pellet burner or something like that, and it leaks a little bit, that's another way in which particles can come into the indoor environment. Dr. Farmer mentioned a couple weeks ago, things like candle burning. Anytime you burn something, you're going to make particles. And so that's the direct emission. And then kind of the final way that we tend to see particle mass or particle composition coming into the indoor environment is actually kind of an indirect source. And what I mean by that is gases, which can either be emitted from surfaces in the indoor environment or come into the indoor environment, can either react and form other chemicals which then go into the particles, or they themselves, these gases, can get into the particles and add to that total mass of particles in the indoor environment. And we've seen this for things like phthalates, which are plasticizers. They can come from vinyl flooring. We've seen it with siloxane species. These are in like heat seal and silicone. And we've seen it with residual cigarette smoke in a non-smoking classroom. And I'll get to that a little bit later in my talk too. So those are kind of the three general ways in which particles can come indoors. This infiltration from outside, direct emission from activities, cooking, burning, things like that, and indirect sources, is gases getting into particles. And what that means chemically is we'll get into later in health aspects as well. So the infiltration, how outdoor air gets inside. I talked about infiltration in your home, but there's also other types of buildings. So if you don't live in kind of a single person home and you live in a building, maybe an apartment complex or something like that, you'd have an HVAC system that mechanically controls the ventilation in the building. And so in that situation, this could be an office building as well, you actually actively bring in outdoor air. And when you do that, you have a little bit more control over how that air comes in. You can put in filters, so you immediately filter the air before it comes in. It's not something you can do for the cracks in your house. And you can treat that air. You can heat it up or cool it down depending on where you are. And I think probably in Fairbanks, you're going to be doing a lot more heating than you are going to be doing cooling in a mechanical ventilation system. And then going back to your home, infiltration through doors, windows, cracks, that's the typical way that air comes into those homes. And then if you have an HVAC system or some other kind of whole house fan, something to move the air around in your home, you can get recirculation inside, but you're not actively bringing air in a home situation typically. And so this leads to differences in filtration or recirculation and air exchange rate. And one thing that we have typically found, and this is kind of a general rule of thumb, this isn't necessarily 100% of the time, but we almost always see lower particles indoors. And usually it's about half to a third of the total particle mass outside is what comes in. So on that exchange from bringing outdoor air to the indoor environment, you lose a significant fraction of that total mass. And so the concentrations typically are lower from infiltration. Now, the cooking, smoking, or burning anything in the house will add to that and may increase the particle levels in your home higher than what is outside. But if it's just air being exchanged between the indoor and outdoor environment, you're typically going to see lower concentration indoors than outdoors. The other thing to think about when you bring outdoor particles into the indoor environment is temperature change. So when it's cold outside in the wintertime and you heat up the indoor environment, there's a pretty significant gradient in that outdoor to indoor temperature. And that can change the composition of particles. There are chemicals in particles outside that when you heat them up, those chemicals want to come back into the, they want to come out of the particles and go back into the air. And so what ends up happening is you lose some particle mass from that outdoor to indoor transport through that temperature change. And we studied this in a classroom in Philadelphia, and we published a couple of papers on it. But I think the really unique thing about Fairbanks is that the temperature gradients we see in the mid-Atlantic and Philadelphia and Baltimore, where I am now, are not anywhere close to what we're going to see in Fairbanks. And I think that that temperature gradient, you know, of almost 75 degrees Fahrenheit or 40 degrees C between outdoors to indoors is really going to lead to some interesting differences in the chemistry of the particles that we see. And I'm really excited to use the instrumentation that we have in my group to kind of explore that change next year in the wintertime. And so that begs the question, you know, if there are these different chemicals and they respond differently to temperature gradients and the chemicals in there, what are they made of? And I think this is fundamentally what the research in my group has been doing for quite some time. And it's something that we've done, not only our group, but a bunch of groups all around the world in the outdoor context. And so this is an example from a paper over 10 years ago now, where this is just a comparison of the chemical composition measured with the instrumentation we have in places all around the world. We've got some stuff in China and Japan, in the US and Europe and Canada and Mexico, and in different seasons. And you can see the colors in the pie charts, the proportions change, which means the chemical composition of these particles, while they share a lot of the same types of things in them, the relative fractions of them change depending on where you are on the globe. And that's related to the sources, it's related to the season and what chemistry might be going on in the outdoor environment. And it's a really important thing to understand from an air quality perspective, because if we can identify the sources of all these different chemicals, then we can start to say, okay, if we want to reduce the number or the total amount of particles in this particular area, and traffic is the dominant thing that's contributing to them, then we should, you know, increase our regulations on vehicle emissions or something like that. And so understanding the composition of particles helps us design policies to improve the air quality. And this is, again, is in the outdoor context. In the indoor context, we can't really regulate what people do in their homes, but since infiltration is an important factor in terms of what gets into the home, we can still regulate things in outdoor air quality to improve the indoor air quality of what is being breathed by people in their homes. And so this is infiltration. So if we think about what's coming in from the outdoors, we've got this variety of chemical composition that's going to be dependent on the place that you are and the season that you're in. And that's what's coming in from the outdoors. And then again, in the indoor environment, you've got your direct sources. You've got cooking. A lot of that could be cooking oil. You've got wood smoke if you have a wood stove in your home and you're using it. if you smoke, cigarette smoke and residue, and there's other chemicals, the residues that can lead to additional changes to the composition of particles that we see in the indoor environment. So this is going to build a little bit from what Dr. Farmer talked about 2 weeks ago. My group also participated in the home chem project, which she described. And this is an example from one of the mock Thanksgivings that was done in June in Austin, Texas. So it wasn't a true Thanksgiving because it wasn't November. But when you cook all day in a house, you generate a lot of particles. And so this graph on the right that you see in green is the organic material in the particle phase. And this dominated the indoor particle composition. It was 95% of the total particle composition. And so this is the total organics, but that organics material can actually be subdivided into different chemical classes with the instrumentation that we have. And if we do that, we can separate out these different chemical species and look at them as a function of time. And so this green, when we subdivide it into these other factors, we call them, gives us an idea of what's in the particles. And so this darkish color is this anhydrous sugar. This looks like burning carbohydrates. It's actually pretty similar to if you burned wood or if you burn bread or something in the oven. They look chemically pretty similar. Factor 2 in this lighter green color is kind of small. It's like a cooking oil, but it looks more like animal fats. This factor 3, which dominates the total, looks a lot like cooking oil. So if we were to take cooking oil and put it straight into our instrument, it would have a very similar chemical signature to what we're seeing there. And finally, this gray factor that I'm showing at the bottom, this tended to go up when we had oven use, and it wasn't really present when we didn't have it. So this was related, we think, to the oven use. And we know that because during the home chem project, we took very copious notes about what was going on at any particular moment in time. And so this is that same Thanksgiving meal over the course of the day and the cooking from 9 a.m. all the way to 6 p.m. and those different factors plotted versus time. And then we have marked on here what was going on at the particular time. So again, that factor 4, which is related to oven use, preheating the oven, putting the pies in the oven, we saw this increase in that factor. And then when the pies are being taken out of the oven, I'm sure some of you may have experienced this, if you tilt them a little bit and all that fruit in the inside is a little bit liquidy and it spills out and splashes out on the oven door when you're taking it out, you get a little plume of smoke that comes up. And that's actually what happened here. And you see this increase, very rapid increase in what we call this factor 1 from those pie drippings hitting the hot oven door and kind of smoking. So chemically, we know exactly where that came from, and we can see it reflected in the instrumentation and the measurements of our instrumentation. When we put the turkey in the oven, you can see the slow buildup of this dashed thing. This is the oven use factor going up and up and up. Added some Brussels sprouts to the oven. I think opening the oven door increased that factor a little bit more. Oops, went too far. Another kind of fun thing to look at, one of the oven mitts was placed a little bit too close to one of the burners on the stove, which is a propane burner, and it caught on fire. And so we saw another little blip of this burning factor. And so sugars from pies, the cellulose that makes up an oven mitt, those things burn, produce pretty similar chemical signatures. Again, not that surprising given what we understand about the chemical structure of those species. So we can see pretty clearly that there's a variety of different chemical compositions that happen over the course of the cooking, and they're not all the same, and we can identify differences between them, which is interesting to think about the particle composition from this factor. In the context of FairAir and just in general, wood smoke is not something unique to Fairbanks, and wood smoke pollution is certainly not unique to Fairbanks. This is a picture of Rovereto, Switzerland. And so after I did my PhD in Colorado, I moved to Switzerland for a few years and worked in a lab there. And one of the issues in Switzerland, especially in these mountain villages, is wood smoke. And so we did a lot of detailed investigation of wood smoke when I was living in Switzerland and making measurements of that too. So it's something that I actually am pretty interested in and have a little bit of knowledge from this experience in Switzerland. And one of the one of the papers that came out of this was a PhD student that I helped supervise, was we looked at the emissions from logwood burners, wood stoves, and pellet burners. And really, this is just kind of this fancy sciencey headline for this paper is just another way of saying we just measured the smoke that came out of wood stoves and pellet burners in a laboratory in a very controlled fashion with a lot of really expensive equipment. And it was nice to understand that and learn more about what was going on at the time. And I'll get back, we actually had another group from Australia who was there, and they did some health relevant measurements that I'm going to talk about a little bit later during this project as well. So wood smoke is something that's important to think about, and its composition is different. And then the third piece of the indoor emissions that I wanted to touch on and not maybe leave too much or get into too much detail is kind of these residues that can be left behind. Certainly, if you can smell something, it's there. So I know that, if I go camping and I'm sitting by a campfire and I come back to my house and I pull my clothes out of my backpack and I smell them, they're going to smell like fire. They're going to smell like campfire. And that smell is semi-volatile species that will come out of my clothing over time. And those gases that we can smell can also go into the particles and add particulate mass. And so if you can smell it, it's definitely there. And so it's not only like that with wood smoke, it's also like that with cigarette smoke. And this is something that we learned doing our indoor measurements in Philadelphia in a classroom. And in a classroom that had not been smoked in for 30 years, we found about a quarter or 25% of the indoor particle mass was due to residual cigarette smoke brought in by people who were smoking outside and working in an office that shared the same HVAC system, the same ventilation system as the classroom we were making the measurements in. And so this gets to an important point that what happens in one room in a house or a building that has recirculating air, what happens in one room can actually affect other rooms in that house. And I think this is one of the concerns right now with COVID and how that can be spread in the indoor environment is moving air around between rooms and in other places, and thinking about how to protect people in these different spaces. And so one of the focuses in right now with COVID is to really improve the way that we filter and handle air in the indoor environment. So this was a really interesting finding, and we wanted to investigate it in more detail with this residual smoke because we wanted to kind of really prove to ourselves that this is what we were seeing. And so what we did was we did some lab tests to confirm that this mechanism, this residual smoke, when it gets on a surface, can actually come back off of that surface, get into the particles and add additional mass and change the composition of those indoor particles. And so what we did was in our lab, we smoked a cigarette in a hood. We didn't actually smoke it ourselves. And we brought that smoke from the cigarette into a glass jar. We let it kind of sit there for a couple minutes, and then we pulled all the air that was in that jar out so that the air was clean. There was no more smoke in the air, but some of that smoke and some of those particles from the smoke had settled onto the surface of that jar. And so there was a residue of that smoke still in the jar, although the air from the smoke was no longer there. It was just what was on the surfaces. And then what we did was we took outdoor particles and we measured those directly with our instrument. And then we also took those exact same outdoor particles and we brought them through the jar so they could collect some of the chemicals that were, coming off of the surfaces. And we measured the particles after they had been exposed to that jar. And we compared the chemical signatures of the particles that hadn't been through the jar to the ones that had been through the jar. And we were able to replicate the signature of that residual smoke that we saw in the classroom. And so this is what, in the scientific community, we call third-hand smoke. So, primary smoke is what you breathe if you're smoking. Second-hand is if someone else breathes. And third-hand is if this smoke gets on surfaces and then comes back off. That's the third-hand smoke terminology that we use here. And so that's just one more mechanism by which particle composition in the indoor environment can be affected by, what has happened in a room in the past. And I think this brings up a really important, point. And I think this is something that a lot of people are concerned about, is how bad are they for you, right? So we know that smoking is bad. And if smoking particles can contribute to the composition that we breathe of particles indoors, even if we're not smoking, is that something to be concerned about? How do we understand which types of particles are the worst for us? And the answer is, we have some ideas, but it's not something that's been fully, I think, developed. And I think there's still a lot of interest in really identifying which particular components of particles are the worst. But the reality is, the way that we measure and monitor particles in the outdoor environment is by total mass. We don't have all of the tools and techniques to do a full assessment of particle composition across the globe easily. It's expensive to do the type of work that my group does and other groups do. And it's too expensive for a regulatory network like the ones that EPA runs to do all the speciation to the kind of molecular level that we really need to understand the health impacts. But what we do know is that the concentration of outdoor particulate matter is directly correlated with mortality rates. The higher the level of outdoor particulate matter that people are exposed to on an annual basis, the higher the mortality is in those regions. And it can be traced back to those particulate matter concentrations and pretty clearly and easily developed or shown through many, many studies. This has been replicated quite a few times by different authors and different ways of looking at the data. So this is a very robust relationship. We're very confident that minimizing our exposure to total PM is going to improve our life expectancy. That being said, we also know that, especially in the US and Europe, and when it's really cold outside, we spend the vast majority of our time indoors. And so our exposure, again, to this outdoor PM2.5 that we know is correlated with mortality and increased mortality the higher the concentration, our exposure to that outdoor particulate matter actually happens, for the most part, in the indoor environment. And this, again, is going to be due to that infiltration. So that's one thing that we know for sure. And I think really the question, and this is something that my research group is starting to pivot to start to think about and work with people at Hopkins to understand in more detail, is how the different chemical components in that PM, how toxic they are. And I think the short answer to the question of, is PM equally toxic, is no. And again, it's this inability to measure individual components across many different locations to build up the statistical data sets we need to really identify which components are the worst is difficult and expensive, and it hasn't really been done to the level that it needs to be done. That being said, we do measure some components of PM under the regulatory framework. And one of those components are polyaromatic hydrocarbons. These are PAHs. If you know what those are, they're known carcinogens. They can cause cancer. And we measure those in some regulatory context to understand those concentrations, especially in urban areas. There have been many studies also showing that traffic-related particles have a much higher toxicity and have a bunch of health impacts, including neurodegenerative diseases in the elderly populations. And then there are additional health-related properties that people are starting to study in more detail, looking at reactive oxygen species. So these are things that can react relatively quickly and oxidize things in your body. I think a good example of that is if you've used hydrogen peroxide, that would be an oxidizing reaction. If you pour that on a wound, you see kind of the bubbling action. And particles, although very, very, very small in mass, and we're talking about, 100 times smaller than the width of your hair, a little bit of reactive oxygen species in those can also be problematic if you breathe a lot over an extended period of time. And so we want to measure those and understand what relationship, that concentration of reactive oxygen species may have with things like inflammation. And so there are a number of groups around the world looking into that and trying to understand that. But I think it all comes back there. There is some intuition that can go into this too. You often find high particle concentrations near an ocean, and a lot of that has to do with crashing waves. Some of that is sea salt. Some of that is organic material that's resuspended. Is that going to be as toxic as diesel exhaust? Probably not. I don't know if those health studies have been done directly comparing those two things, but I think intuitively we would much rather be breathing that than the tailpipe of a diesel truck. And then things like cooking oils are another thing that's probably relatively benign. I had asthma growing up, and the inhaler I used actually used oleic acid as one of the components of the inhaler to help stabilize the albuterol, which was the medicine in that inhaler. And oleic acid is the major component of olive oil and canola oil. So I used to be basically breathing cooking oils when I'd have an asthma attack, along with the medicine to help relieve my asthma attack. So I think cooking oils are probably things that are going to go in the less toxic category in comparison to things like diesel exhaust. So we do know that there are going to be differences with the chemical components of particulate matter. And I think these are studies that we need to go into and do in more systematic investigations of. That being said, that same experiment that I mentioned before, where we were measuring the smoke coming out of wood stoves and pellet burners, the group from Australia was measuring this reactive oxygen species content of the wood smoke coming out of these burners. And one of the findings that was really interesting was that per mass, so if you took 1 particle unit of wood smoke and compared it to 1 particle unit of cigarette smoke, the wood smoke had about 4 to 9 or 30 to 80 times more reactive oxygen species than cigarette smoke. So on a mass basis, wood smoke has more reactive oxygen species than cigarette smoke. But keep in mind, you're not, inhaling a piece of wood like you would be inhaling a cigarette. So it's not quite a fair comparison, because you'd still be getting a lot more dose from a cigarette than you would be from wood smoke. But it does say something about that wood smoke containing some reactive oxygen species in it, and much more so than cigarette smoke on a mass basis. What was interesting in that study as well, though, was the pellet burners, which also burn wood, but in a pelletized form and under much more controlled conditions, didn't have any measurable levels of reactive oxygen species. So that may also indicate that the manner in which you burn things and how efficiently you burn things actually can change the toxic or the reactive oxygen species content of those particles. And so that you may have less health impacts from things like pellet burners than you would from things like wood smoke. And this is, again, just one study, and it certainly warrants additional attention, but it was an interesting finding and something that I wanted to bring up as, if you have a choice between pellet burning and wood smoke, this is an option potentially for thinking about what might make less of an impact from a health perspective. And I think finally what I wanted to do to kind of wrap things up is, ultimately, we want to limit our exposure. And the things that you can do in order to limit your exposure are, minimize your indoor sources. Now, I'm not saying you shouldn't ever cook. I think cooking is actually something I enjoy doing quite a bit. But you can certainly, if you have the option, turn on a vent fan, or if you have the option to use electric burners, it's better than using a gas burner. You can't always do that. So if you can't minimize those sources, ventilation is important. So whether that be with a vent fan or opening a window to let a little fresh air in after cooking, it's not a bad thing. I understand right now it's probably a little bit difficult with it being very cold outside. And then finally, another option is filtration, whether it be a filter in your whole house. If you have an HVAC system that kind of recirculates air in your house, you can turn the fan on and kind of pull some air through that with an appropriate filter, or if it's an in-room air filtration unit. Then I'll give a couple examples of what that can look like. So one thing that I wanted to just touch on is the the MERV rating of a filter, and this is for something like your heating unit in your home. If you have something like this, you can choose an appropriate a MERV filter. And so what this graph is showing is how efficient particles of various sizes are removed by MERV rated filters. So a MERV 16 filter removes almost all of the particles, the really small particles, and it drops down to about 70% efficiency at about 200 nanometers or 0.2 micrometers. And it gets back up to about 100% efficiency of removing particles by that kind of 1 micrometer range. Dr. Farmer mentioned, I think in her talk a couple weeks ago, that the respiratory droplets with coronavirus are kind of in this kind of 1 to 2 micron range is kind of where we think they are. And so kind of any of the MERV rated filters in this range that remove 90+% are something that's going to be protective if there's coronavirus floating around in the air. And so just in the context of the pandemic that we're currently living in, it's always something to think about. So in my home, we use MERV 12 filters, and that does a pretty decent job removing a lot of the particles and dust which may be floating around our house. Something that you can do if you have a system that pulls air through your whole house. And not every house has that. And so, there are other options like in-room air filters. And so, this is something that it's a unit that you can move from room to room, and it has the ability to pull air into it through a filter and then put filtered air back into the room. And so ultimately what you want to be able to do in a situation where you want to clean your air is know kind of how big the room is and buy the appropriately sized air filter for that room. You do want to avoid things like that advertise ozone or UV or some kind of oxidant, because this often can lead to introducing chemistry into your home that you don't necessarily want to happen. And really a HEPA filter is going to be sufficient for the most part in removing particles from the air. The key in choosing the right kind of in-room filter is going to be this clean air delivery rate, and all reputable in-room air filters will have this value given to you. And so, just a comparison of various models on Amazon, you can get smaller ones which do about 230 meters cubed per hour. And this is really annoying to me because they're actually switching back and forth between feet and meters. But I did the calculation for you. This says it covers up to 500 square feet. The reality is that's only for 2 air changes per hour at this volumetric flow rate and assuming an 8-foot ceiling. And what you really want, especially in the context of COVID again, is about 5 air changes per hour. And that helps really filter the room and remove particles and, if they're present, coronavirus. So in reality, a 230 meters cubed per hour will only really filter about 150 square feet with a 5 air change per hour clean air delivery rate that we're looking at. And so, these are some of the ways in which you can kind of reduce your exposure to particles in the indoor environment and protect yourself in the current pandemic. So I just kind of wanted to summarize and give you guys kind of a perspective of where we're coming from and what we're excited to do in Fairbanks and better understand things. And so I wanted to just put this up as just a typical day in a home, and you're looking at PM concentrations if you measure them indoors with maybe a purple air or something in your house. And what you see, in the morning, let's say you get up early, you make breakfast around 6, you see the spike of particles from breakfast cooking goes away, and maybe something in the evening. And you want to know, over the course of the day, what different activities are leading to the kind of particle mass that you're breathing in your home. And so we can kind of color code things. And what I'm showing here in green is now this outdoor particle infiltration coming into your home. And that's going to kind of go with what happens in the outdoor environment. So that goes up and down kind of with rush hours. And then surface repartitioning, when these outdoor particles come in, they can soak up some of those those chemicals from the indoor environment and add to that total mass. And that's what this yellow is. The cooking breakfast and dinner, assuming that you're not home at lunch, which probably isn't the right assumption these days. You see these increases in the breakfast and evening times of that cooking. And if you clean up after dinner, you get maybe a little bump from that cleaning. Now, in the context of wood smoke, that might add more in the indoor environment. And that's another emission that we'd have to think about in the context of FairAir, and something that we're looking forward to doing again next winter. But we can also then take this and we can sum up over the entire day how much of the particle mass that you breathed in during that day came from outdoors, and about half of it came from outdoors in this context. About 20% came from this repartitioning of residues on surfaces, about 30% came from cooking, and about 1% came from cleaning. Now, that chemical complexity that I've been talking about and showed a few examples of, we really want to understand how each of these different sources may have different health endpoints, respiratory issues, cardiovascular problems, all sorts of things that can be associated with particle exposure. And so my, feeling is that each one of these is probably going to have a different effect that we have to investigate in more detail. And then ultimately, as much as I like doing measurements, there's no way we could measure in everyone's home at all times. And so we also then have to work with modelers and take what we observe in our measurements and think about how to model that across many different homes and different scenarios. And maybe someone has a different infiltration factor in their home versus someone else. And we can use models to explore that variability between people's homes much more easily than we can do measurements in everyone's home across all of the different possible permutations of the way people's homes are set up. And so part of what we have to then do is translate our measurements into this modeling framework too. And that's something that we want to do more. And we've been working with modelers to do that as well. So I hope, I gave you a general overview of all of these different things that we've been thinking about in my group, and hopefully made it interesting for you to learn about. And I'm at this point really excited to hear what questions you might have and see if I can answer them.
Great, thanks. Thanks so much. That was very exciting talk. I see a number of questions coming in. So Kelly, you want to pick a couple or pick one?
Sure. Let's see. I've got one person, a couple earlier this talk asked, can COVID-19 aerosols or droplets attach to air particles like PM2.5 and 10 or other particle pollution? If COVID can attach to particles, what level of public health danger does this create, and how long might these particles be viable into health danger?
It's a good question. I think, so when particles attach to each other, what we typically see is really small particles doing that to larger particles. COVID particles by themselves are large enough that they're probably not going to attach to other PM2.5 particles, but they'll be in the air at the same time. And so I think there have been some studies showing that higher levels of PM2.5 and higher levels of PM10 can be associated with worse impacts or higher transmission rates of COVID. It's not clear what the mechanism is for that, and it may be due to the PM2.5 and PM10 being more respiratory irritants, and then the COVID coming in and exacerbating those problems. But I don't think attachment of those two things is really the mechanism by which it's getting into the body. I think it just gets in because it's big enough to do it by itself.
Okay, and kind of along that line, we have another question that says, how effective are COVID face coverings at blocking PM2.5 particles?
It's a great question. Is it a cloth mask? Is it KN95? Is it there's so many different permutations of masks that you can't say with definitive answer how good it is for each thing. Now, what I will say is that masks are really good at getting at filtering your breath going out, and there's another reason for that too. So you guys, it's really cold out there, so when you breathe and you're outside, you see this like cloud of fog coming out of your mouth, right? your lungs are moist. They're covered with moisture. Your body is at about 100 degrees Fahrenheit. And so when that warm, moist air comes out and mixes even just immediately with cold air, you have these rather large droplets. And so those sizes of particles are pretty easily captured even by basic cotton, like 3 layers of cotton masks. And so that is protective to other people. It's also going to protect, to some extent, particles coming in when you breathe too. They won't be as large as the droplets coming out of your breath. But these masks are certainly a layer of protection that you want to have at all times. Now, if you can get N95 mask or a KN95 equivalent, that's going to be something that offers even more protection. But these masks will filter PM2.5 in exactly the same way that they filter COVID. It's particle physics, and the mask doesn't know the difference between a COVID particle that's 1.5 micrometers in diameter and a air pollution particle that's 1.5 micrometers in diameter. It's the same physics that's going to intercept both of those particles.
Okay, another question. Any sense of how outdoor particle matter from other circumpolar regions is circulating around the circumpolar north, and how much of our outdoor PM is locally produced?
It's a great question. It's transboundary air pollution is an issue at all latitudes. And so, certainly in the polar regions, in the wintertime when it's dark, you can get, air transported from Russia, from Canada, coming back around. And my sense, looking especially at, this FairAir project has made me look into this, and also, have a lot of conversations with people like Bill, who have studied this in much more detail. But generally the concentrations in Fairbanks, if you're not burning a bunch of wood, are really low. And so in general, you're not getting a whole lot of contribution from other places. And most of it, by far, the vast majority is going to be locally produced. You could probably, get 10 miles out of Fairbanks and away from where people live, make measurements, and you'd see very, very, very pristine conditions. And I think just that gradient from Fairbanks to 10 miles away gives you an indication of how much is really just locally produced.
Yeah, or the other thing we see is when the wind comes up, it really cleans out.
Yeah.
I see another question, which I'm not sure if it's quite along your lines, but I'm interested in if you've got an answer. Somebody has a Harman pellet stove with a catalytic converter and has no advice from the manufacturer about how to know whether it still works. Does it work after 10 years? Or how do you know?
That's a good question. I don't have a lot of experience with that. I mean, catalytic converters are, from a science perspective and an engineering perspective, they're supposed to essentially last forever. They provide a surface for additional oxidation reactions to occur. And so what they are intended to do is anything that doesn't burn fully in the pellet stove should further burn, in a sense, on the surfaces of the catalytic converter. That being said, I know that when we were doing measurements in Switzerland with a vehicle, we were just idling the vehicle over and over and over and over again. And what is known, we fouled our catalytic converter. So it didn't work properly because it never got up to the temperature it needed to get to work efficiently. We drove it on the highway at some point, and it burned off all the stuff that had collected on the surface, and it started to work again. And so I think as long as you're using your pellet stove at its normal operating parameters, the catalytic converter should continue to work properly. That being said, I mean, you could make measurements, but that's very expensive to make, and see that. But I think it's probably a safe bet that it's working at some efficiency, or some reasonable efficiency at this point.
Kelly, you see another one there?
We have a quick question. Do passenger airplanes change 5 air changes per hour?
They do more. So this is one of the things, like air travel. The biggest danger of air travel is probably not, and this was, I think, a study that came out a few months ago, is not the airplane itself, because the airplanes have very, very good air handling units. They've had to for a very long time. So they have HEPA filtered air at about 10 to 12 air changes per hour, which is 2 to 2.5 times what's recommended. The biggest danger is actually probably going to be like in the airports themselves, when you don't have as much air change and you're bumping into more and more people.
Okay, how about, so we have our major electric company in Fairbanks burns diesel at some plants and coal at others. The exhaust lingers in the air during the cold times in winter. What does that mean for the particulate matter levels? And can you point this person towards references that can better inform what implications coal and diesel burning may have?
I'm going to point them to Bill.
Okay, Bill, this question's
No,
in the Zoom chat.
I mean, I can say my 2 cents, and I know Bill has thought more about this, but in general, the strategy for air pollution has been to build stacks. So, if you exhaust your burning at a much higher level, it gives it a chance to disperse before it kind of gets back down to ground level where we're breathing. In the wintertime, we have a lot of inversion layers, and I know Fairbanks has some pretty strong inversions. And so a lot of times what happens is that those emissions are actually emitted above that inversion layer, and they don't make it back down as frequently to the surface as they would in other seasons. That being said, they can obviously still impact air quality, and it depends really on the meteorology at the time. But it's something that that's certainly on our radar, and it's something that we want to investigate with all of the expensive instrumentation that we're all bringing up next winter. And so, I can let Bill, further answer this question, but I also want to say this is a TBD thing based on some of the studies that we're planning to do.
Yeah, I just want to reinforce that, this study is really nice, that we're going to get in experts like Pete and others who have really state-of-the-art instrumentation that can really more finely separate what's in the particles than the routine measurements that were done. So I think we're going to learn a lot about that he can see more tracers in there. There was also a question about coal. I think the question was really about an indoor coal stove and what particles might come into a house. And we may or may not be able to do that depending on whether the house that we rent has a coal stove. Nonetheless, do you know of good tracers that you have for coal that might be able to look at, we'll be both measuring outside and inside air to see what influences there may be of coal burning out in the outside air? Do you have some good tracers for that?
So, I mean, my general recommendation is try not to burn coal indoors if you don't have to. And I understand that that's not always possible. But coal is one of the more, it depends on, I guess, the quality of the coal that you're burning. And along with that comes the level of tracer that you might expect. All coal has some level of sulfur in it. And so one thing that you would see from burning coal, and we, my group has made measurements in Nepal where coal is heavily used in industry, and there's no after treatment of that. And so what you see with coal direct emissions is a lot of sulfate or sulfur in the particles. So that's something that we would see. And if we're doing tests in a house next year where there is a coal stove, we can really, one of the nice things about having something like that is we could actually make measurements directly of what's being emitted and look directly for those chemical signatures then in the outside air when we're measuring in general, and see if we see those same signatures in the outdoor air that we see in the indoor air. In Nepal, we did identify a couple tracer species in our data set that were linked very strongly to that coal burning from the brick kilns in that region.
Great. Yeah, and so this is a little bit of a plug that we are going to be renting a house next winter in order to do these indoor and outdoor studies. And if people know of houses, please get in contact with us, because we're looking for a really representative house in the Hamilton Acres neighborhood. And we'll be in contact with the community more, but just to plant a seed there, if you know a good house, maybe with a coal stove in it, that would be quite interesting. Kelly, did you see another good question?
Yeah, it looks like we've got 2 more questions. What effect does using a wood stove have on indoor air quality? Not sure if we've touched on that already.
I mean, that's a great question. And you know, the reality is there's no I think every wood stove and every wood stove installation, more importantly, is unique. I don't know if you can see behind me, but my house, which I just moved into this past summer, has a nice wood stove that I have not allowed my wife to use, even though it's semi-cold in this room, because of some of the work that we've done. And I've considered getting a pellet stove, but I think the reality is, you know, how leaky is the wood stove? Does it have a catalytic converter? And not just the wood stove, but the exhaust for the wood stove, is that also potentially leaky? Because if you're getting a little bit of smoke penetrating into the indoor environment, then that's going to add overall to the concentrations in your house. If you're really just getting the heat from the wood stove and all of the smoke is going outside, then you're going to get a little bit coming back in from that outdoor environment, but you're not going to get as high concentrations indoors. And so it's a combination of kind of the technology level of the wood stove, how well it's been installed, and how leak tight everything is. And I think all of those factors come into play in what the indoor air quality impact from that wood stove is going to be.
Cool. Well, thanks so much. We're kind of heading to the top of the hour here. I see there was a question about radon, and we'll try and answer that on the in the FairAir website. There are a lot of great resources that the state has with respect to radon. I don't think that's something you really do much with, Pete. So I think we'll get some resources to you through the FairAir website with respect to radon. And I just wanted to wrap it up first by thanking Pete for a great talk, and thanking the whole community for all their great questions. As I said, any questions that we didn't get to, we'll put up on the FairAir website, so you can take a look at the article about this event. The next talk is going to be in 2 weeks, and it's going to feature Professor Emily Fisher from Colorado State University, talking about wildfire smoke and the health impacts of that. So thanks so much for joining us, and have a great night.
Thanks for having me.
Thanks, Pete.